Let's get it started with Chapter 1. Chapter 1 lecture. We will be moving through the chapter, not breaking these lectures into individual sections. So we're going to start with measurements and significant figures, which is the basis for Chapter 1. Make sure you have your notes and you are following along, annotating as you see fit. Feel free to press pause so you can make those notes. Let's see. So first we're going to start with the scientific method. Steps of a scientific method. First, make observations. They need to be quantitative and qualitative. Quantitative meaning numbers. They have to deal with how much of something there is, and then qualitative meaning the types of observations that you're making. And formulating a hypothesis of why those things are the way they are is a possible explanation of the observation that you just made. And then perform experiments based on your observations and your hypothesis. An experiment is carried out to test that hypothesis. This involves gathering new information that enables a scientist to decide whether or not the hypothesis that they just made is valid. That is, whether it is supported by new information learned from the experiment. And experiments always produce new observations, and this brings the process back to the beginning. So, outcomes over the long term. You're going to get things like theories, also known as models. You hear the word model used a lot more today than you have in the past. But a theory is a set of tested hypotheses that give an overall explanation of some natural phenomenon, explanation of why this thing occurs, and that's very, very important. As opposed to a natural law, you know, things like the law of conservation of mass. The law of conservation of mass is simply an observation that applies to many different systems. We're not just talking about chemistry, we're talking about mathematics, we're talking about physics, we're talking about biological systems. These same observations that support this law of conservation of mass is observed over many different systems. Now, the big difference here is that a law just summarizes what happens, whereas a theory or a model is an attempt to explain why. Okay, this is the big difference between the two for our purposes. So, what ends up happening is a law is something that's not questionable. This thing definitely happens. A theory is going to be very questionable. We're very much going to dig into this, whether or not it makes sense. We're going to try to gather data to try to test whether or not our hypotheses are correct, and then change those hypotheses based on our observations and our experimental data. So it's the theory, or the model is the thing that gets constantly tweaked throughout the process of science, or at least it's supposed to when science is being done well. Here's the example that we have. Gravitation. We have the law of gravitation. Okay, the law of gravitation. Definitely things when they go up, they come back down. Not just that, but any two objects that have mass exert gravity or gravitational attraction on each other. That is a law. This happens over many different systems. You can observe this happening. But the theory of gravitational attraction, the theory of gravity, at least as far as Einstein is concerned, or his theory of gravity, it describes gravitational forces in terms of the curvature of space-time caused by the presence of mass. The greater the mass, the greater the distortion in space-time. And Einstein is the person who came up with the term space-time to try to identify space and time as not being separate entities, but combined in the same thing. Now we're moving on to a measurement. Okay, so we're going to start getting quantitative. We're going to start getting some calculations up in here. So an observation is a quantitative, again, numbers, quantitative observation consisting of two parts. First part is a number, and the second part is a scale. It tells you what scale we're talking about here. We also call this a unit in common conversation. So some examples. If I have 20 grams, I have a number. The number is 20. I have grams. That's a scale. I'm telling you I have 20 watts. A unit is grams. I also have 6.63 times 10 to the negative 34th joule seconds. The number here is 6.63 times 10 to the negative 34th. That is a number. The scale or unit, the qualitative thing I'm talking about, is the joule seconds. So here is a table. The quantity that we're looking at, they have the common SI units or the base SI units for each of these quantities and then their abbreviation. For mass, it's the kilogram, even though gram is going to be a little bit more useful for us in chemistry here. Length is the meter. Time is the second. Temperature is Kelvin, even though we will be working mostly with degrees Celsius. The SI unit, the base SI unit for temperature is Kelvin. For electric current, it's amperes, amperage. The amount of a substance, which we'll be working with a lot, is the mole. It's how much of a substance you have. And then a luminosity, or the intensity of luminosity, is a candela. From these base units, these 7 base units, you can derive any and every unit that you need from that. So if you've heard of a unit of force, a Newton. It's a unit of force. It is derived by multiplying kilograms by mass, by length. I'm sorry, not by length. What am I talking about? Kilograms divided by meters per second squared. That is a Newton. A Newton is a unit of force. We have pressure, stress, pascals, pressure. We have newtons divided by meters squared, and on and on and on. Joules, watts, coulombs, degrees Celsius, lumens, ohms, volts. What else we got? Tesla, hertz. All these different units are units that we are going to be using here and there, but they're all derived from these 7 base units. Now let's move on and talk about temperature here a little bit. Oh, went too far. Go back. The 2 types of temperature that we are going to be using in AP chemistry is the Celsius scale and the Kelvin scale. And both of these are names of men that way back in the day were selling thermometers. All right, and the reason that these 2 types of thermometers caught on is because they both used water as their basis, and because everyone has access to water, it's a very common thing. It's very useful. People understand what those numbers mean, so they base their scales on water. Now, their starting and end points were a little bit different. For example, Fahrenheit, he made his scale, the freezing point of water, 32 degrees Fahrenheit, 32 degrees. He made his boiling point of water 212 degrees, whereas Celsius made his scale, the boiling and freezing point of water are 100 degrees apart. You have 0 degrees Celsius for the melting point or the freezing point, and then you have 100 degrees Celsius for the boiling point. And so we see the difference between freezing and boiling on the Fahrenheit scale is 180 degrees. That's the difference. Whereas the difference between freezing and boiling on the Celsius scale is 100 degrees Celsius. Now, we're not going to be using the Fahrenheit scale. We will do a few conversions here at the beginning of the course, but as we get going, we're just going to use the Celsius and Kelvin scale. The Kelvin scale is actually much more useful for describing the kinetic molecular theory of motion, which is one of the things that we'll cover. That describes the motion of matter, particularly the electrons and other small particles. And the 0 mark for Kelvin is 0 Kelvin. And by the way, notice there's we got degrees Fahrenheit here, degrees Celsius. There's no degree sign right here. You don't say degrees Kelvin, you just say 0 Kelvin. 0 Kelvin is absolute 0, the temperature, the point at which there is 0 molecular motion. Okay, all things stop. Okay, that temperature has not been achieved in the laboratory. Incredibly close, but it has not been achieved in laboratory and does not exist in nature. Temperature is very, very close. Very deep space, incredibly cold, but not quite 0 Kelvin. The same temperature on the Celsius scale is negative 273 degrees Celsius. That is absolute 0. On the Fahrenheit scale, negative 459 degrees Fahrenheit. But again, we're going to be looking at the Celsius and Kelvin scales. You will need to be able to use the prefix system, the SI prefixes, to convert back and forth between different units or different scales in this course. So you have mega, kilo, deci, centi, milli, micro, nano, and pico. Of these, the ones that we are going to be using the insane most is going to be kilo, centi, milli, and micro. Okay, those we definitely need to have those memorized just off the top of the head. You will have access to these prefixes throughout the unit. However, you may not have access to this during the exam. So make sure you get used to these during your practices. Moving on to that uncertainty in measurement. So a digit must be estimated. Sorry, a digit that must be estimated is called uncertain. If you don't know it for sure, with absolute certainty, it is uncertain. It has a degree of uncertainty. A measurement always has some degree of uncertainty because measurements are performed with instruments, and no instrument can read an infinite number of decimal places. So at some point, that next digit is going to be estimated, is going to be uncertain. So there always is some amount of uncertainty in measurement. To describe that, we're going to use two terms, precision and accuracy. Accuracy refers to the agreement of a particular value with the true value. Now, in order to assess accuracy, you will need access to the actual value, the true value. But what you're doing is you're comparing your value to that true or known value. Precision, and even though in common conversation we use precision and accuracy pretty interchangeably, this is not common conversation. This is science. This is AP chemistry. Precision refers to the degree of agreement between several measurements made in the same manner. Now, in science, you don't just carry out one experiment. You do several. You repeat many times, and that's how professional science is done. If you do an experiment 5 times, how closely those 5 measurements agree with one another is described in terms of precision. So if we use the good old-fashioned example of a bullseye with some arrows, if I have this particular grouping of 3 shots, I'm not very accurate because I'm not very close to the bullseye, and I'm not precise because I'm hitting in 3 different areas of the target. Here, I have a pretty close grouping, but I'm not very close to the bullseye. Okay, so my grouping is close. So that means that my precision is high. It's precise, but it's not accurate because, again, I'm trying to hit the middle of the bullseye, and I didn't really get all that close. Now, if I have a tight grouping, okay, if I reproduce the shot pretty darn well, and they're all grouped in the bullseye, that is precise and accurate. Now, there are some different types of error that you need to be aware of because during this course, you will make errors. And it's important for you to differentiate between the types of error. Silly mistakes, something like plugging a number into your calculator wrong, you need to understand that that is a very strong possibility. You will do that at some point during this course. How many times, I don't know, but you will do it. And you want to compartmentalize these different types of errors because these different types of errors deserve or warrant different responses. So there is a random error, also known as indeterminate error. It's a measurement that has an equal probability of being high or low. Okay, you're not sure. You're not really sure what it is. Maybe you don't know the true value. You might have missed high or you might have missed low, but you're not sure. There's a systematic error, okay, and it only occurs in the same direction, okay, every time, either high or low, often resulting from poor technique or incorrect calibration. This can result in measurements that are precise but not accurate. An easy thing in my mind that helped me with this idea is when shooting a basketball. When a basketball player becomes tired, they tend to start missing all of their shots short. A lot of the balls that they shoot, they hit the front of the rim. They don't go in. They don't hit strong back iron. They hit the front of the rim. that's coming from a systematic error. Athletically, you don't have what it takes at that moment to make the shot go in. So there's a systematic error. You're consistently missing short. Okay, so you're missing in the same direction each time. As opposed to a random error, if I'm just not good at basketball, if I'm not good at shooting, sometimes I'll miss short, sometimes I'll miss long, sometimes I'll miss left, sometimes I'll miss right. Okay, that's just a random error as opposed to a systematic error. Now let's get into the fun stuff. Okay, significant figures. Hooray. So we need to be aware of non-zero integers. Okay, anything that's not a zero is always significant. Okay, it's always significant in a measurement. For example, 3,456 has 4 significant figures. But zeros, when we're talking about zeros, that's where things start to get tricky. Leading zeros in front of the non-zero digits, they do not count as significant figures. For example, 0.0486 has 3 significant figures because the 2 zeros in front are leading. They are in front. They lead the number. They are not significant. Continue to look at zeros. Captive zeros, sometimes known as sandwiched zeros, in the middle of 2 non-zero digits. They always count as significant. For example, 16.07 has 4 significant figures. So obviously the 1, the 6, and the 7 are all significant, obviously, because they're non-zero. But because that 0 is in between a 6 and a 7, 2 non-zero digits, it also is considered to be significant. Now, trailing zeros are where we get a little bit tricky. Trailing zeros are significant only if the number contains a decimal point. For example, 9.300 has a decimal point. So those trailing zeros, the one in the back, are significant. So that comes in at 4 significant figures. And I should say, if there is no decimal, those trailing zeros are not considered significant. So if I use the same example, but I tell you to ignore this decimal right here, there'd just be 2 significant figures. These would no longer be significant if there were no decimal. I know right there, there is. Exact numbers. Okay, this is going to come into play a little bit when we're trying to consider significant figures, which we will be doing all course. Exact numbers have infinite numbers of significant figures. They do not hinder the number of significant figures that you have. One common mistake is the conversion factor used to go between inches and centimeters. 1 inch is exactly equal to 2.54 centimeters. Exactly. There's an infinite number of significant figures here. There's not 3 significant figures in this number right here. It's infinite. This does not limit the number of significant figures you're going to use when reporting your answer. You're not going to limit it to 3 here. It's infinite. So let's try some practices. How many significant figures are in each of the following? Oh, I went a little fast. My bad. Pretend you don't see that. 1.0070 meters. 1, 2 non-zero digits. Okay, so that's at least 2. I got 2 sandwiched zeros or captive zeros, so that's 2 more, so that's 4. But does this trailing zero count as significant? Oh, yeah, there's a decimal. So, yes, it does. As all 5 digits are significant. Let's look at 17.10. Again, I see 3 non-zero digits, so there's 3 right there. I see a trailing 0. I also see that there's a decimal that makes the trailing 0 significant, so we have 4 significant figures there. 100,890 liters. I have 1, 2, 3 non-zero digits. I have 2 captive zeros, so that's 5 for sure. And I have a trailing 0. But do I see a decimal? No, I do not. So that makes this trailing 0 not significant. So this only has 5 significant figures. Now we're going to look at something that's in scientific notation. 3.29 times 10 to the 3rd seconds. This has no zeros, so it's just 3 significant figures for sure. And by the way, it is a little trick. Any number that is appropriately or correctly written in scientific notation, all digits that are reported here, no matter what, are going to be significant because there's always going to be a decimal here. There's always going to be. So just a little hint, a little easy one for later. Here we go. 0.0054 centimeters. Let's see. 1, 2. But these are leading. These are leading zeros in front. Leading zeros have a rule. They are never significant, so that's just 2 significant figures. I have 3,200,000. I see 2 non-zero digits. I see 5 trailing zeros, but I don't see a decimal, so that's just 2 significant figures. Now, when we are going to be multiplying, dividing, adding, or subtracting significant figures, which we will be doing a lot, there are rules to follow here. The number of significant figures in the result of a multiplication or division problem equals the number in the least precise measurement used in the calculation. So whatever number has the fewest number of significant figures, you use that number of significant figures when reporting your answer. For example, if I multiply 6.38 by 2.0, the calculator is going to tell me 12.78. But I want to use the 2 significant figures from the 2.0, so I'm actually going to have to round this up to 13 so I can have the 2 significant figures that were used in this 2.0. All right, so if I punch this into the calculator, okay, 3.24 meters by 7.0 meters, I get 22.68 meters squared, right, because of meters times meters. What am I going to report, though? I'm going to report 23 meters squared because of these 2 significant figures. I'm going to round this to a second significant figure. I have 100.0 grams divided by 23.7 centimeters cubed. The calculator is going to tell me a big old long thing, grams per cubic centimeters, but I only have 3 significant figures in my answer, so I just report 4.22 grams per cubic centimeter. I have 0.02 centimeters multiplied by 2.371 centimeters. Calculator tells me a big old long number, but I only want to report it with 1 significant figure. 1 significant figure because that's how many significant figures are in this value right here. No matter how awkward it feels to round off the rest of the stuff in the number, you have to round it off because all of this stuff is highly uncertain. 710 meters divided by 3.0 seconds. Calculator is going to give me a very long number, but I'm going to have to round that to only 2 significant figures. Now, here's what I do. I have 236. I need to round this to 2 significant figures. That's this 3 right here. This needs to be rounded. Okay, am I going to go up or down? Well, this 6 tells me I'm going to round it up to 4. But here's the thing. It's not 240 decimal because that would make this 0 significant. So to still maintain my 2 significant figures but be as close to this number as possible, I'm going to go 240, no decimal. No decimal. Let's try another one. My calculator is going to tell me this big old long number, but how many significant figures do I want to report? 3.23 feet. Okay, is the value with the smallest number of significant figures. That's 3 significant figures. So I'm going to report my answer with 3 significant figures. Round to this 7. Okay, this 2 tells me to keep it the same. So 5,870, no decimal. Let's do a couple more. I got this big old long number the calculator tells me. What am I going to round this to? I'm going to round it to 3 significant figures because of that 2.87 milliliters. And I end up with 2.96 grams per milliliter. All right, let's look at addition and subtraction. Okay, the rules for that one. They are a little bit different from multiplication and division. Addition and subtraction. The number of decimal places in the result equals the number of decimal places in the least precise measurement. So here we're just looking at decimal places, okay, places past the decimal. For example, in these 2 values, I have 1 place past the decimal and then 3 places past the decimal. So I have to find the least precise measurement, and that is the 6.8 because it's only one digit past the decimal. So my calculator is going to tell me 18.734. But because I can only go 1 place past the decimal, I'm going to have to round to this 7. This 3 is telling me to keep it the same, so just 18.7. That's 3 significant figures. Let's try these practices one more time. So calculator is telling me this long number, I only want two significant figures. I only want one digit past the decimal place, so I'm going to round to 10.2. Plug this into your calculator. It's going to tell you this number. How many places past the decimal do I want? Oh, one place past the decimal. So one place past the decimal, one place past the decimal. Looking at this calculation right here, I got two places past the decimal over here. So I'm going to need to go two decimal places past the decimal here, two digits past the decimal place. Here's my next calculation. Only one digit past the decimal place, one digit past the decimal place. Next calculation, I look over here. I only have one digit past the decimal, so I'm going to go to here. I'm going to round this up to 0.6. Good to go. Here's my next calculation. I have 1, 2, 3 places past the decimal. 1, 2, 3 places past the decimal. Ooh, what do I do here? Okay, what do I do here? My calculator is just telling me 0.16, but I want three digits past the decimal place. What do? I add an extra 0 to the end of the number. Now I have 1, 2, 3 places past the decimal. And I'm not adding a number. I'm not changing the value because it's a 0. It has a value of 0, but it is holding a place and it is showing you a certain amount of precision. All right, guys, that's going to do it for part 1 of your Chapter 1 video lecture.